What's going on, everybody? This is Mr. Diamond, and we are now, yes, counting is hard, so my numbers are a little bit off. We're backtracking now. We did just do Chapter 6, but we are now doing Chapter 4, unless you're watching this future, in which case, welcome to Chapter 4, or whatever number this chapter is. This chapter is over circular motion, circles and stuff was kind of the subtext for this one. We're going to start with Section 1, thinking circular. We need to actually make sure that we can know what it's like when you're thinking in something that is a circular in motion as opposed to something that's linear in motion. Now that we're in the realm of circular motion, we can use pretty much the same type of stuff that we have been using. We just have to do a couple of minor tweaks. We're going to start with some of the most important variables, velocity and speed, and we're going to talk about acceleration a little bit later as well. Distance and time are not as big of a problem, but there's some other little stuff in there as well. Our previous definition will still hold up in this case. Speed and velocity are still related to distance and displacement, respectively. Speed is distance over time, velocity is displacement over time. However, when something's traveling in a circular, you can't just measure it as a point A to point B. So instead of being told an object is traveling X meters in Y time, we'll now be thinking in terms of, well, what's the size of the circle the object is making? Is it making a small circle, a bigger circle, or a gigantic circle? And the reason for that is because if a circle, if you're moving in a straight line from here to here, you just measure this distance. But if you're moving in a circular path from here to here, well, it matters if the circular path that you're taking is going to be a little bit different to calculate. So let's start with a simple thought. You have a circle that is currently spinning 10 rotations per second. We may think that that's rotations per second. That's like a distance, kind of. So that's a good speed or velocity unit. And really it's useful, but it leaves a lot of information out. And we can prove this because the size of the circle really greatly affects it. Think about the Earth. The Earth is a gigantic sphere, and if you just think of your position on the Earth, that is a circle that's rotating. But that circle that you're rotating on takes 24 hours to complete one rotation. We know the Earth is moving fast, though, but if we scaled that down and we had a record on a record player that was rotating at a speed so it took 24 hours to make one rotation, we would expect that to be an issue. I just realized my mic is really far away, so I hope that you've been able to hear me. If not, well, I'm probably not redoing this video, but we'll see. I guess whenever I watch it, we'll see how bad it is. But a record player rotating at that speed would be abysmally slow. But we know that the Earth is actually rotating at a speed that equates to thousands of miles an hour. So it has to do with the fact that the distance it's covering to make that full rotation on a record compared to literally the Earth is a lot bigger. So rotations per minute is actually giving you something closer to what is called angular speed. It's how fast the relative angle of an object is changing over time. So if you think of the Earth as a big circle and you move from here to here, that angle change will scale down to the angle change of the record player. And they should be changing at the same angle. Whenever the Earth has gone through 1/4 of the day, it's done a 90 degrees out of the 360 of a circle. You would expect that that 1/4 of a day, the record would also be 1/4 of the way through rotation. So in 24 hours, in our example, the angular change would be 360 degrees, or to be more scientific, 2 pi radians. When I say more scientific, the real reason for this is because degrees is actually made up. We learned throughout all of school that 360 degrees is how many degrees there are. That number was just selected because it's a number that subdivides very, very easily into multiple parts. So 360 is kind of just a made-up number. Radians is related to the arctangent and some other weird trig stuff that I don't remember from whenever I took that class in high school. So radians is a more scientific measurement. So if you're using angles whenever you're talking about physics, you're probably going to be in radians. So to measure since we know that the Earth is moving faster, we know that we need to calculate something else. So let's actually figure out the distance that it travels. Well, the record, if it's a circle, if we think of a point on the outside of that circle, when it goes one full revolution, it has traveled all along the outer edge of that circle. So really, we can just use our equation for what is the distance around a circle, and we actually have that. It's 2 pi r. A circumference is equal to or the radius times 2 multiplied by pi, or the diameter of a circle times pi. And you will be using the pi key for this. Don't round it to 3.14. So that will allow us to calculate the distance traveled. So if we know how long it takes to make one rotation, And if we know how long it takes or how much distance is traveled in one rotation, we can use that to figure out the speed. So this is going to be our equation we use. I know this r is capitalized, but normally we would do it lowercase. Velocity is equal to 2 pi r, so that's the distance over. Now, instead of it being lowercase t for time, this is actually supposed to be a capital T. This is because it's called a period. It's represented with a capital T. So we said earlier that let's take our circle rotating at 10 rotations per second. That means that it also completes one rotation every 0.1 seconds. It takes 0.1 seconds to complete a full rotation. So if we do this, we can actually plug that number in, that 0.1 second per rotation. 2 pi r is the distance per rotation. The rotation part will cancel. We'll be left with distance over time. Bada bing, bada boom. We got ourselves a velocity. So that's what the equation we'll use for finding velocity when we're talking about circular motion. Two examples that I'll work out. Example 1, we've got determining the velocity of an ant resting on the edge of a 0.305 meter diameter record spinning at 45 RPMs. And then the hint I'm going to give you is that to convert between frequency and period, they are the inverse. So one is rotations per second, one is seconds per rotation. To convert between them, you can just use 1 over t equals f or 1 over f equals t, and that lets you flip-flop back and forth between them. So I'll solve this one. And then our second example is going to be an object placed on a disk is moving at 25 meters per second on an object moving, and the object is moving at 10 rotations every 25 seconds. What is the distance from the center point of the disk that object must be? Now, the wording on this is a little weird, but when we're talking about things in circular motion, if you have a circle that's like a gigantic one right here, but something is further inside of that circle, like it's only halfway across it, it's technically still making a circular path. The radius of that circle is just smaller than what the radius of the full circle is. So we can actually just, even if it says it's a 10 meter across disk, you can be standing 5 meters across or 5 meters away from it. I guess if it's 10 meters across, that's diameter. So you could be standing like 2.5 meters away from the center, in which case you are halfway across the disk, halfway across the radius. That means that you are still technically traveling in a circle, but the circle you're traveling in is just a smaller than the larger circle you're actually traveling on. We'll look at some stuff on the board that may make this be a little bit more clear. But that's going to be our second example, and that's all I've got for today. Just look for those videos down below in the other section. In the meantime, though, if you've got any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.